Welcome to the HVAC-Engineering-Techie channel. This is the channel where we talk all things HVAC. We talk about engineering design, we talk about construction, we talk about equipment, we talk about systems, controls, we talk about HVAC extensively, and we also talk about system performance. So today we're talking about heat load calculations for technicians. This is calculations when you're trying to figure out how big a unit, how big a coil, or how big of load you're going to have in a certain room or building. And we will talk about that to give you a little background education on how engineers actually do this. You probably won't do this very often, but this is the information for you to have it. Before we get started, I'd like to ask you a big favor. Would you mind becoming a subscriber by hitting the subscribe button down below and the like button, the thumbs up? These cost absolutely nothing. It's absolutely free. You'll never be charged for anything, and you'll never be bugged by me for anything. It's just that Google uses those numbers to tell how valuable this video is and how it's being used. And it would be a personal favor to me, and I'd appreciate it if you do that. So let's go ahead and get started on heat load calculations for technicians. So now we're going to talk about building heat gain or heat loss calculations. So most heat gains are calculated by using a computer program. And the reason is there's a whole bunch of repetitive calculations to do this. And they want to do a whole bunch of data with these calculations. What I'm going to show you is how to do it manually. How you can do it manually. It's very tedious, but it is capable of doing it, especially if you're trying to check something or do one room or do something like that. You can do that. The main programs that I'm familiar with is Train Trace. Carrier, I think it's called 7000, and I'm sure there's others like EQuest and others you could actually run a heat gain on. These are not free pieces of software, so you have to buy them. So I would only recommend you buy one if you do this all the time. The heat gain or heat loss calculations are done by multiplying each of the building's directional surfaces, square footage, by the combined material U factor times the temperature difference of the inside and outside surface, including effective sunlit materials. So this is how you do it. You break the wall down, but you need to understand heat gains are not perfect because walls and roofs and ceilings are not homogeneous. There's places that are denser than others, little places better insulated than others. So these are all average guesses, and you just try to get the best guess you can to be able to get the best information you need to do your job correctly. A rule of thumb is that cooling normal space without, this is commercial building of course, without sunlit windows is around 1 CFM per square foot or 30 BTU per square foot. And the rule of thumb for heating a normal space is around 0.65 CFM per square foot or 39 BTU per square foot. And this is for mild ambient conditions, for summers 95 to 100 degrees, winters 10 degrees to 30 degrees. This is not for the frozen tundra north, nor the blistering summer deserts. That they'll be different, but these are just rules of thumb. So if someone asks you, do I have enough air conditioning for this space, office, and you find out they have half a CFM square foot, the answer is no. They have 1 CFM square foot, could be, might not be, but could be. If it's a space that has a lot of internal high heat gain or sunlight windows, the 1 CFM is no longer correct. It'll take more. That's why we run heat gains, to find out what the real value is we need. Okay, the basic process. You select design conditions from ASHRAE 1% data or local weather data. Normally we use 20-year average data, but you have to be a little careful with that as things are getting hotter around the world. 20-year data may skew it to be on the low side, so you may want to look at what a 3-year average looks like and a 20-year average and use your numbers accordingly. Ambient temperature, you need ambient temperature, the humidity, and the humidity ratio for the exterior, and then you need the indoor temperature, humidity ratio, and ratio for the inside. Those are the things you need to be able to do a heat gain. So standard U factors are exact U factor for the materials manufacturer, or you add up all the resistant factors for materials in a wall or roof construction. And then U is 1 over R. So if you got the resistance, you just add them all up and divide 1 by that, and you get a U factor. Now, standard light convection conversion factors from table for type of light fixture. So you need to figure out how many BTU per watt these light fixtures give off. Now, in the older days when we had T12 fluorescent lights, it was a bunch. It could be 2.5 watts a square foot. Nowadays with LEDs, we're down around 0.5 watt a square foot, so it's changed a lot. But the interesting thing I've observed is when I first started back in the 60s, we had 2.5 watts for lights and we had 0.5 watt for plug load. Nowadays, it's 0.5 watt for light load and more than 2.5 watts for plug load. And of course, that's due to computers, because computers has driven up our plug load substantially, especially if you have a data center on site in your office or something like that, or a lot of data closets. They can drive up this plug load considerably. So lighting is done in watts to BTU, standard humidity vapor transmission factors from a table. So not only do you need U factors for the walls, you also need humidity vapor transmittance. How much moisture is going to come through those walls? And this is a little bit different, but you have to know those. You just know the humidity ratios between inside outside, and that gives you the velocity pressure. It gives you the humidity pressure, vapor pressure, and that vapor pressure will come to the walls unless you have really good vapor barriers. Now, unfortunately, in buildings today, most of them do not put vapor barriers in buildings. They put air barriers, but not vapor barriers. So you have to be a little careful with that. And then sensible heat equals area, square foot, times the delta T times the U factor, and that gives you the BTU of the heat transfer. Separate walls and windows by direction. So you want to have one of these heat gains for the south, the north, the east, and the west. And then also what you want to do is calculate the latent heat, which is people plus the outside air plus vapor through the structure. And also on the sensible load, you want to calculate windows that aren't sunlit and then add the sunlit portion of the window, because the sunlit portion has a whole bunch of heat. So what we try to do is we try to keep direct sun off the windows if at all possible, with outside shades or trees or something, because sunlit windows put a whole bunch of heat into a space. And then solar transmittance through sunlit glass, what I just said. You enter glass twice, once for convection and once for radiated heat. So basically, sun on the glass causes lots of issues. You can use sunscreens to dim this down a little bit. But these are all the things that we figure when we're trying to figure out what a heat load actually is. All right, so now I'm going to show you this manual sheet here. And it's just something that I've used for lots of years to quick check a heat gain or a heat loss. It's really a dumb sheet. And I'll go through what areas are which on it. And then I've given you a clip of what the equations look like in this. And if you want to create one, you're more than welcome to, but it's nothing special. So here we go. First of all is number 1, which is this data up here, right here. And this is the design conditions for ASHRAE, or local weather, which has the outside temperature, outside wet bulb, and the outside humidity ratio, and the inside conditions also are up here. Number 1, the outside conditions are up in here. So it's just 2 rows. And now this sheet you have to use, this is not smart, right? So like a computer program, it would figure it out for every hour of the day, 24 hours a day, 365 days a year to give you a heat gain. This is an instantaneous. It does for 1. So if you want to look at a summer load, peak load, use a summer design day, and then you have to do it again for a winter design day so you get your heating load. So they operate differently. So it's really dumb, but it does show you what goes into it. So basically, that's 1 is the ASHRAE local weather data. Standard U factors or exact U factors for materials. That's what these right here. These are all the U factors you got. So here, first of all, we have the directions, your surface areas. Here's the square footage of those surface areas. And then these are the factors, and this is the U factors. And I put a bunch of U factors in here that are standard. To be quite frank about it, U factors don't make a lot of difference. If you're 0.1 or 0.05, close. If you're 0.9, it makes a big difference. But basically, for most walls, you're going to have some. These are standard walls, And so I've listed those standard walls in there. You won't go wrong if you use these. They won't be perfect. You wouldn't want to use this sheet for a big job, but if you're checking water just doing a small job and you don't want to run a big program or you don't have a program, this will work. So 3 is a standard light factor. So these are right here. So this means a fluorescent, LED, whatever kind of light you have. These are the watts per square foot we normally see. And these take place over here where you put the square footage, check your watts, and that's where the heat's generated over there. Standard humidity factors, that's off of your table up here. And then right here is the standard humidity factors from the table. So this is going to tell you what transmittance you're going to have, and these are used down here in the radiant calculation, or the latent calculation are used up here. 5 is a sensible heat, so that's right here. So the sensible heat is all these factors simply calculates the fresh air and the outside air is in here. And it comes down and it gives you the total heat and the total sensible heat factor within the building. So that's added up all these things because of the sensible heat. 6 down here behind me where I'm talking to you is all the latent heat. And this is where we have, sensible heat has people and has outside air. Down here it has people and outside air again because these are both the conditions that cause latent heat inside the building. So, and vapor through the structure, which is these calculations coming up here for vapor. And then vapor is for package units, see the bottom figure in gold color. For FANCO, use CFM, sensible latent heat numbers. So what it happens is right down here, it calculates total load for an air handling unit. So it gives you the total CFM, the total load of the coil, grand sensible heat factor, all those things you might want to look at a unit. And then again, up here is 7 is sunlit glass. So what I did is I kept the square footages separate for a glass. So east glass, north glass, south glass, and west glass all have 2 rows. One is for conductance only, and the other is for sunlit. And then these are the sunlit factors here. These are out of an old design guide. This has been surpassed nowadays, but I still use it because I'm familiar with it. It's easy. Tells you what that is going to be. And then this is a total heat gain. So this is for your air conditioning side. Then you run it again for heat loss. And you do exactly the same thing, but you change the parameters to winter condition. And then you don't have to change much of anything else except you change the outside. And then you have to look down here. There's some things that will generate heat, and you have to decide whether you want to include those in your heat loss calculation or not, like lights. And the reason I say that is because you can't turn off the lights. Years and years ago, we used to have a design philosophy in our I'm in the Southwest, so I have real mild temperatures, where we were having big office buildings that they heated with the heat of the lights, because the lights were 2.5 watts a square foot, so they have a lot of heat. So they just leave the lights on all night, and that would heat the building. Well, then the revolution came, and we went to T8s and the T5s, and then the LEDs, and those buildings were no longer heat. So I had to come in and retrofit supplemental heat because it took a lot of heat out of the building. So if I was designing a building, I would take out of the heat loss calculation, I wouldn't let the lights add any heat. I would put the heating system be capable to heating the building without the lights, because they may not be there. And the same goes for people. People add a lot of sensible heat, but they may not be in the building. So I would not allow the people to have heat either. Then I'd have just the heat of the structure so I could do it. So those are the manual things you need to manipulate on the heat loss side. So, and then of course, if you want to see it at different times of the year rather than peak design, you'd have to do more than one of these. Now, years ago, before we had computer programs, I have done buildings where I have done 12 months of every zone in the building, and it take me literally days and days and days to do heat gain because I'm doing it all manually. And by the way, that was before computers, so I was doing all this on a calculator. Anyway, much better nowadays. Now, here's a sheet with the formulas exposed. And I'm going to disappear for a minute and talk to you by not being on there. At least I think I'm going to. Maybe not. I'll move out of the way, and you can see these formulas. You can take a clip from your screen, and these formulas are all exposed, and you're free to use this. The only thing is, I'm telling you that this is a sheet I created for my own use, and I have no warranty or guarantee. Use it at your own risk. But if you want to see all the formulas, they're actually exposed on this sheet, and you can do that. So that's basically how we do heat gains, heat losses, and even if they're a fancy computer program, they're still the same. All these numbers, back in the day, I've written several programs to do heat gains when I was doing a lot of large jobs. And before anyone had one to sell, we created our own and run them on the big old IBM computers before mini computers or microcomputers were out. So I know this is the right process because we've used that and we've made programs to do that. So anyway, I hope this was helpful. That's how you do that. So that's basically it. So hopefully heat gains, if you're going to do those, you have some fun doing that. And please don't forget to subscribe and like. And I hope you enjoyed this. Catch you on the next one. Thank you.